Hello and welcome to Lesson 3 in what is an extensive series covering various different examples in the C++ programming language extracted from various different books I have read. Now before I forget to mention this, I will say this at the start of this particular lesson, and that is that the next lesson will take place most likely not this weekend but the next weekend, as a consequence of the fact that I have to actually formulate the paper regarding an overview of the C++ programming language, and in particular I need to formulate what I would refer to as a generalized model capable of encapsulating the behavior of all possible C++ programs, and that will take some time, and so preferably I would like to do that this weekend, but if that is not possible, it will be the next weekend. Although it perhaps doesn't matter at this stage because there isn't much viewers of these videos at this particular stage. Now, I would like to begin this lesson also by mentioning the following, and that is that in the interest of being succinct and making this lesson as short as possible, I will not necessarily discuss all relevant details relating to the various different facilities that we use. So for instance, I could spend time discussing how the standard library move function is implemented in order to give a more enriched understanding as to how it fits into particular programs. That could be done, but instead I think I will prefer to put it this way. I will attempt to discuss all relevant details relating to the implementation of today's program, but I perhaps will not go into as much detail as would be desirable, and so consequently, if you have any trouble understanding certain things that are being talked about in this lesson, then just comment down below and I can help you out. So that's the first point. In the interest of time, I will be and in the interest of brevity, I think is the word, I will be discussing all the relevant details as required, but perhaps won't go into significant technical detail in terms of how the various different facilities are implemented. So that's what I would like to say before I begin this lesson. And I suppose I'll mention this before we begin. By the way, I hope this lesson will be shorter than the last lesson. The last lesson was roughly about 6 hours, and I think that my approach, I prefer the approach that is thorough and gives detailed descriptions of the various different procedures and steps that are being taken. I think that, and especially from a learning perspective, I think that that can be beneficial in some cases. I actually forget what I was going to say. Anyways, before we begin, I would also mention this. So in terms of formulating that paper regarding an overview of the C++ programming language, it will also contain a subpaper detailing the type system and of course a general overview of the language itself, not just necessarily a generalized model. So that's the first point. So with that being said, let us begin today's lesson. And also, I will say this, I'm taking quite a long time in this introduction, but it is relatively short when compared to the length of time it would take to do this lesson. I would like to mention the following, and that is that I will be developing various different components in order to provide a solution to the specified problem in today's lesson. And with respect to that, I would like to do that as fast as possible because today's lesson is a relatively simple example of the implementation of what's called a vector. And so consequently, I don't think much time needs to be spent detailing the various different procedures in relation to its implementation. And so consequently, I will try to be as fast as possible to get through this so that the lesson is relatively short and you get an understanding of how to implement a basic vector. So with that being said, let's actually get into the substance of today's lesson. So, a programming language represents a means of expressing solutions to problems. Thus, we identify a problem and undertake the task of writing a series of instructions organized in the appropriate manner that results in program behavior that is in accordance with what we require of our abstract requirement specification. In relation to the latter, this is the prerequisite step for actually implementing the solution, encoded as a series of suitably organized instructions. We refer to the process of implementing solutions as devising logical structure. The most obvious question that arises when considering this is something comparable to the following. How do we actually go about the task of writing the necessary instructions? That is, how do we devise logical structure? In particular, is the process a scientific one, or perhaps more elegantly described as an art? First, we must define what we mean by scientific. First, all development and discoveries we associate the term science with, irrespective of their superficial complexity, are derived from a single fundamental pillar we describe as an axiom, and this axiom is perhaps the most beautiful piece of human logical reasoning to ever have been conceived, and yet is so simple despite that. It can be stated thus. First, we construct what we call a theoretical representation that attempts to describe and encapsulate the behavior of some specified system. We then provide input to this representation and compute the consequences. Now, if we repeat the process again, but this time on the real system in question, by providing analogous input, and subsequent observation of how that system behaves is in accordance with our theoretical models, then the representation is to be accepted as good until supplemented or superseded by subsequent representation. Although not necessary for our purposes, we should perhaps extend our discussion to include yet another one of humanity's most profound pieces of logical reasoning. That is, theoretical representation, with respect to its physical interpretation, need not be in accord with human intuitive perception of how the universe functions, so long as the theory makes predictions for quantities that are in principle observable, and observation shows agreement between the representation and the behavior of a particular system. In this sense, devising logical structure is very much so a scientific exercise, in the sense that we create a series of instructions organized in some specified manner and devise an interface to this arbitrarily complex internal structure by means of a mechanism for input. Then, we should be able to observe some output given that input. Now, for any given input, if the results obtained through extensive testing are in accordance with our abstract requirement specification, then that logical structure is to be accepted as good in a manner analogous to a hypothesis with which we associate the term scientific. However, you may have justifiably observed the following. What of the actual implementation of the logical structure itself? Well, its composition in and of itself can perhaps be accurately categorized as something of an art. In this sense, this process is not, in its totality, guided by a scientific method. However, specific components may use the scientific method, and furthermore, we may actually be implementing a scientific process in code. But, with respect to the latter, it still remains very much so an art. However, having stated this principle, that is not to exclude the possibility of the formulation of a rigorous scientific theory that can guide the development of programs at some point in the future. Now, in relation to devising logical structure, how do we do this? In accordance with the observations made in Lesson 2, we construct an algorithm specification, the design of which results in program behavior that results in fulfilling some desired logical objective. We then set about the task of identifying the various language and library facilities that, when combined, can be used in the implementation to elegantly express the intent implicit in the design documentation. This is a skill acquired through extensive practice and experience. So, what's all this discussion about? Well, It is related to the fact that in today's lesson we will be discussing the implementation of something called a vector, which is an entity that must which is essentially an entity that must provide a means of expressing collection of objects and provide various different operations for manipulating this collection. Thus, we must implement various components that work in unison to form a facility that can be used to solve programming tasks. We will make reference to the notion of logical structure and its composition throughout the lesson. Now, in relation to the point that was just made, I think there are two primary notions of logical structure. There's a notion of logical structure which essentially relates to the formulation of a specific algorithm that performs some specialized task, and then there's also the notion of devising various different components which can be regarded as algorithms that work in unison to solve some specified problem. So there are two primary notions of logical structure, and we will make reference to that throughout the lesson. One second. I'm just going to write down the time just to make sure, just to track how long it has been going on for. Okay, so what is today's lesson about? We wish to implement what is called a vector. So, what is a vector? A vector represents a mechanism for expressing a collection of objects of some type where the amount of objects is dynamic, that is, it can change. Now, the comments I'm about to make perhaps seem unjustified unless you have the knowledge and experience to be able to understand the principle that is about to be stated, or the technique that is about to be stated, but I will nevertheless proceed to do just that. In terms of implementing a vector, one technique that we can actually use is to essentially regard the vector instance as being a handle to a dynamically allocated chunk of memory, and that dynamically allocated chunk of memory stores a series of objects of some specified type. And in order to provide the semantics of dynamicity, we need some mechanism to change the size the size of the memory that stores the various different objects. And if we were to use a built-in array to represent that block of memory, then quite frankly there is no direct mechanism for obtaining that behavior. And so consequently we need to emulate dynamic arrays, because built-in arrays are not dynamic in and of themselves. And so we need to emulate dynamic arrays, and one way to do that is to essentially repeatedly reallocate the vector with differing array sizes in order to emulate that effect of dynamicity. But we will get on to discuss that throughout this lesson. In today's lesson, we won't necessarily be dealing with an implementation that makes use of the notion. We will make use of the notion that the vector acts as a handle. In other words, it doesn't store directly in its representation the series of objects that constitute it. Instead, we regard the vector as being a handle to some resource that stores these objects. And in terms of our implementation, we won't necessarily directly observe the notion of built-in arrays, but this is actually quite a useful lesson. And I suppose in preparation for this lesson, I didn't just want to implement the solution. I wanted to actually discuss what a vector is and what operations it performs, because I think that was necessary. And so this lesson will take the chance to do just that, such that in the future, when we cover slightly more sophisticated implementations of vectors, I can refer the viewer back to this particular lesson, such that they can gain an understanding of what a vector represents. And in that way, they can then have a more enriched understanding of the implementation in future lessons of the vector facility. Okay, so in relation to the discussion about the fact that a vector represents a mechanism for expressing a collection of objects, in order to achieve this objective, the vector implementation must implement procedures that provide sufficient memory for storing a series of objects. Or alternatively, in order to maintain state information of various objects, we need memory to store the appropriate values. Thus, the vector implementation must devise a strategy to achieve that objective. And the last point I would like to note in relation to this, for the moment being, let me just check. Okay, one more point I would like to make is that in terms of the standard library implementation of a vector, it is actually a template where we parameterize the type that the vector represents in terms of the objects that it can store. And the most obvious use of the template mechanism is essentially to provide a general solution to which we can apply various different types, so long as those types adhere to the constraints imposed by the implementation of that template. Now, with respect to class templates, so long as you don't use a particular member function that performs some operation with respect to a data type with which that particular facility was instantiated, so long as you don't use that operation, then it isn't instantiated, and so consequently we can have a situation whereby a class template defines various different member functions that perform some operation on the type with which it is instantiated, but if that operation isn't supported for a particular type, that need not concern us so long as we don't use that particular member function. Because if we were to do that, it would instantiate it, and that would lead to a compilation error. Okay. So, in relation to devising logical structure, the model that the implementation uses is contiguous blocks of memory equal in size to a multiple of the size of, in terms of the amount of memory a particular type takes up in memory, the size of the type the vector can hold. And so let us draw a diagram here to represent what this means. Essentially, we are to regard the vector as being a handle to a contiguously allocated block of memory. And that contiguously allocated block of memory stores a series of objects that can be accessed by means of their relative index position. And so in this particular diagram, we are essentially trying to represent the notion of a contiguous block of memory that currently stores 3 values. Note that we're actually storing 3 values, but by means of observing this particular portion of the diagram, we can actually see that there's more memory allocated than is necessary to store the amount of values, the amount of objects in this particular case. And in particular, we refer to this as reserve capacity. Now, essentially the idea is to define a pointer that points to the first element in the array, and the implementation of the vector supports various different operations. One of those operations is a size operation. A size member function that returns the amount of objects that the vector currently stores. It doesn't store directly in its representation, but in practical terms, the amount of objects it stores. And then we also have a member function called capacity. And capacity is a member function that returns the maximum amount of objects the vector can hold before what we call reallocation. And in this particular case, in order to compute the size, and this is verbose notation, but we will use it nevertheless, taking into consideration this diagram, to compute the amount of elements, we essentially define a value initialized to 0, and then we say that the size is computed as the sum from 0 to 2. We employ the use of the summation symbol of x plus 1. And so in this particular case, the size will be 3. Size will be assigned the value 3. This isn't technical code, it's just a verbose notation to demonstrate what the size is to be regarded as in terms of its value. Now, here's the important point to understand. This particular diagram represents our implementation strategy, which is essentially to allocate chunks of memory that are contiguous. And that contiguous blocks of memory stores objects that are adjacent to one another in memory. As a consequence of this implementation strategy, we can actually provide fast random access to any element, so long as we have a pointer to the first element in that particular vector. And the cost of computing or obtaining a reference to a particular object is that of pointer addition, and that's it. And so consequently, the idea is that if we wanted to obtain the third element, we would essentially obtain a pointer to the first element, which in this instance is P, and add 3, or add 2. And in that way, we can obtain a reference to the nth element of that particular contiguously allocated chunk of memory. So the first principle is that as a consequence of this implementation strategy, we can provide fast random access, and that is no more expensive than simple pointer addition. If we implemented it, if we had, for instance, a linked list, we don't have that same capability, because the linked list doesn't store its elements contiguously, so it's not as easy to actually compute the nth element of a linked list. We have to traverse it in a sequential order in order to obtain the nth element. And that really relates to the fact that the standard library provides various different containers that support various different they have a common interface in terms of the operations they perform or provide, but they are implemented in terms of not every operation is supported by every container, just to note that. But as a consequence of the different implementation strategies in terms of storing elements of the container, and by container we mean that it is an entity that can essentially contain values. That's what we refer to as a vector as. It's an entity that can contain values. As a consequence of the various different implementation strategies for different containers, for instance list, dequeue, and so on, as a consequence of that, it provides benefits but also negatives. And so it's a matter of understanding what is most important to the application programmer, what is most important, what is the most important characteristics you need your container to adhere to in order to solve the particular task you're trying to solve. Now here's the idea. We have a size member function, one second, and a capacity member function, and we've already described what they represent. And in some sense they are intimately related, because without reallocation occurring, size can never be greater than, in fact, size can never be greater than the capacity. But without reallocation occurring, size can only ever extend to the current value of capacity. And that happens as we continuously add elements to the vector by means of a particular routine. And so here's the question that comes to mind. What happens when we add an element under the following condition? Size plus 1 is greater than capacity. What happens? And again, this is relating to the idea of devising logical structure. We're essentially identifying a particular facility we want to provide, and then we have to compose a set of instructions organized in some logical fashion that solves that task. And so the question is, what do we do in this particular scenario? Well, what we do is we reallocate. And so what does reallocation entail? Essentially, what it entails is that we're going to allocate memory to store the amount of elements equal to the following mathematical expression, where x is implementation defined. In other words, essentially what we're doing here, we need to add an element to this particular vector representation, but there isn't enough memory, so consequently we have to reallocate, and that entails allocating memory sufficient to hold the pre-existing elements, but also the element we're attempting to add. But of course, if we were to do that every single time we added an element, that would essentially result in unacceptable and slow performance. And so different implementations vary in terms of the precise value by which we increase the memory during reallocation, and so consequently we can't necessarily specify it in concrete terms, but the general idea is that we allocate more memory than is required, and that is indicated by the x variable in this particular mathematical expression. Now once we do that, we need to copy the elements from the pre-existing memory, and the next thing we need to do is we need to add new elements, the new element to the vector, to the contiguously allocated chunk of memory, and then we need to deallocate the old space, and that implies running the destructors for the various different object instances and giving memory back to the system, such that it can be obtained by means of future requests for dynamic memory. Now, I was going to discuss this at some point in the lesson, but it is, by the way, in terms of future implementations of vector that will come from the C++ programming language book by Jean StrVec, we will implement routines that explicitly use explicit notation to perform, to run the destructor. And so the question becomes, why do we need to run the destructor? And it's as simple as this, and this relates to today's example. If we have a situation whereby the constructor and destructor pair are extremely effective with respect to the process and the process of resource management. And so consequently the destructor is defined to deallocate any memory that particular object instance of a particular class type allocated. And so consequently, if we for instance had a vector of strings, the strings in and of themselves perform dynamic memory allocation. The destructors of those strings in and of themselves perform the necessary actions in order to give that memory back to the system. And if we didn't explicitly run the destructors, either implicitly or explicitly, then we would have a situation whereby we would have a memory leak, and we will come back to discuss that shortly. Okay, let's get a move on. So if this procedure had to be done in relation to reallocation, if this procedure had to be done every time we wanted to add an element, it would in computational terms be very slow with respect to alternatives, both in terms of other container types and also different implementation strategies. Okay. So, we will begin by taking into consideration our previous discussions, laying out the design of the program in terms of the required representation and procedures that automate fundamental tasks related to memory management concerns. We will then proceed to implement these services in the spirit of our initial considerations in relation to devising logical structure. So, in relation to how the standard vector template is implemented, the first principle, and we've already discussed this, is that it stores its elements contiguously. And so we've already discussed this, but we'll go through it again. In terms of adding elements, we have to ask the question, is space available for that extra element? We have to ask that question in some way. And if the answer to that is yes, then we fairly simply construct the element in first available spot, the meaning of which will become clear as we discuss this. If this is not the case, then we need to reallocate. And we've already discussed the implications of that. That isn't what it entails. It entails obtaining memory, moving elements, freeing the old memory, and adding the new element. So, to model this technique, one second. Okay, so in relation to the memory allocation strategy, which is dynamically allocated chunks of memory, to model that technique, we need some mechanism for obtaining chunks of memory, and so for that we will make use of the allocator class template. Consequently, we shall briefly describe the allocator class. So the first point to note about the allocator class is that it allocates memory that is unconstructed. It's what we refer to as raw memory. And in order to utilize that unconstructed memory, we need to actually construct elements within the confines of that particular chunk of memory. In other words, when we want to add an element, add an object to that particular location of memory, we have to construct an object directly in the space allocated by the allocator. And that is done by means of a call to the construct member function. And we will discuss the details of that shortly. Now, when we want to remove an element, we need to call destroy. In other words, we have this dynamically allocated chunk of memory within the confinements of which we construct an object instance. But suppose that we want to actually destroy an object constructed in that space. Then in order to do that, we have to call the destroy member function on a pointer that points to a chunk of memory allocated by an allocator. And the destroy member function essentially operates by running the destructor on the pointed to object. Now here's what's important to understand in terms of our implementation strategy, and that is as follows. Freeing memory is a two-step process. You have to run the destructors, and we do that by means of a call to the destroy member function. We have to run the destructors on each constructed object, and then we have to actually free the memory, give it back to the system. Now, if we unilaterally just freed the memory, then in that case, we wouldn't run the destructors on those instances. And if those instances dynamically allocated memory on the free store or any other kind of resource, the destructors of which perform the necessary actions to clean up that mess, then in that particular situation we would essentially have a memory leak. And so consequently, it's a two-step process. We have to run destroy on pointers that point to objects we constructed in space allocated by an allocator in order to run the appropriate destructors, such that that frees them any memory that needs to be freed to prevent a memory leak, and then we actually deallocate the space and give it back to the system for later use. So, we will discuss the details of that momentarily. The details of what allocator represents momentarily. We're just laying out some of the foundations in terms of our implementation strategy. So, in our design, the representation will consist of 3 pointers that point into the allocated chunk of memory, in accordance with the following diagram. So let's draw a diagram to represent this. We have this dynamically allocated chunk of memory that stores its elements contiguously and adjacent to one another in memory. And we refer to this as unconstructed elements And so the representation will essentially contain 3 pointers. The first pointer is called elements. And elements points to the first object in that dynamically allocated chunk of memory. The second pointer is called first free, and it points to the first spot within the confinements of that chunk of memory that we can actually construct an object in. And so by implication, the implication is that first free essentially points one past the last constructed element in that particular block of memory. And then the last data member is capacity. We're going to call it cap. It corresponds to the word capacity. Capacity points one past the last. Capacity points just past the end of the allocated block of memory. 1 second. Okay, so we also define utility procedures that deal with the task of managing the dynamic memory, each of which, of course, has a name and an associated description. Okay, 1 second. So we're going to discuss various different utility procedures that we're going to be implementing that help to automate certain tasks that need to be performed in certain contexts. The first is called alloc_n_copy. And the job of this particular procedure is to allocate enough space to hold a specified range of elements and copy those elements to that space. The next utility is free. And what free does is it destroys or runs the destructor on the constructed elements and deallocates the space indicated by the state of the current representation. The next procedure is called CHK, standing for check, _n_alloc. And it's essentially implemented in terms of the following logical notion. We essentially check if the capacity is equivalent to size, the size of the vector, which in other words is saying, is the amount of objects we constructed at a maximum given the amount of memory we allocated? And so this isn't necessarily the code we're going to be writing, but it's a general way to represent the particular check that we're trying to perform. If that's true, and what has to be understood is that this particular utility procedure will only be called in contexts whereby we need to check that there's enough space to construct another element, because if we just called it arbitrarily, then that would unilaterally cause reallocation to take place. In other words, what I'm implying here is that it's called in context whereby we're attempting to add a particular object to the vector. So if that's true, in terms of its implementation, if this is true, we reallocate. And if it's false, then we do nothing. And next, we have a utility function called reallocate. And the job of reallocate is to reallocate our particular vector type when it runs out of space. At this stage, I'll state the following, and it's as follows. Note, we will call this, in terms of this particular member function, As with the others, we will call this in implementations without explicit qualification. This implies that when reallocate is called, it is done so on behalf of the implicit this parameter. Thus, we modify the representation of the object to which the implicit this parameter refers. In other words, the object upon which we initiated the original member function invocation that in and of itself calls reallocate. Okay. Okay, so with all that in place, let us actually implement the class definition of our vector. Go up here to do it. Now we will discuss the technical specifications and also discuss what the various different components represent. So our class is called, we are declaring a class type, and it's called StrVec. Now the reason for this is that we are not implementing our vector implementation in terms of the template mechanism that would enable us to parameterize the type the vector can store. What we're doing is, to simplify matters, we're just going to implement a vector that can store objects of a particular type, and in this case, it's going to be string. And so consequently, we call the class StrVec. Now, in terms of the class definition, we have public access specification, within the confinements of which we define the default constructor. One second. Those aren't C's. We define a default constructor that initializes the representation appropriately. And our representation will essentially consist of 3 pointers, and we want to initialize them to null PTR. And we've already discussed what these various different variables represent. And in terms of our implementation, a representation that contains null pointers essentially represents an empty vector. That's the means by which we express the notion of an empty vector. Now, as a consequence of what we are writing here, we can automatically infer that, of course, these references to elements, first, free, and cap, those are references to data members of the class type. Now, the next thing that we do is we declare the prototype for the copy constructor. And of course, the copy constructor has a parameter that is of the class type that we are defining, and in this case it's a constant reference to it, both for efficiency, but also because we do not want to modify the source of a copy operation. And so we express that intent by means of the const specification. The next thing we do is that we declare the destructor, the prototype for the destructor. And in this case, what's important to understand is that in order to manage resources, we need a way, first and foremost, as it relates to resources, for instance, taking into consideration memory acquisition. Whenever we acquire a chunk of memory, a block of memory, we need some mechanism to free that memory when it's no longer needed. And in order to achieve that objective, we could employ the use of naked new expressions. And for every new expression that we employ, we employ the use of a delete expression. But the problem with that is that it's error prone, but it's also not exception safe. And so consequently in C++, the most basic and effective means of dealing with resource management in a way that is logically sound but also exception safe is to define it uh, using the resource acquisition is initialization technique, which is to say that we essentially have a constructor that acquires some resource and the destructor implicitly frees that resource or gives it up. And so consequently, we can't. Essentially, what I'm saying is that if you define a class that deals with memory directly, then and that class acts as a handle to a particular resource, you're going to have to define a destructor because the automatically synthesized default semantics of the destructor will not be sufficient to ensure that we don't have a resource leak. So consequently, we have to explicitly define the destructor, and so consequently, that's what we do and indicate by means of the declaration of the destructor's prototype. Okay, so let's just go through this very quickly to make the lesson shorter. We declare a member function returning no value, as indicated by the keyword void, called pushback, that accepts an object of type string. And this represents the mechanism for adding an object of type string to our particular vector. Now the next thing that we do is declare a member function returning a size t, which is an integral type called size, the purpose of which is to return the size or the amount of elements currently constructed in the space managed by the container. And in order to compute that value, we return the result of the following pointer subtraction operation. Now, in terms of, let's perhaps graph this out explicitly. So let's actually go to the bottom here so that we don't interrupt what we're doing there. So essentially what we're doing is, we've already talked about the fact that our strategy employs the use of a contiguous block of memory. And here's what we have to, at the conceptual level, and perhaps in technical terms too, we are essentially to regard the program as having access to a pool of memory. And whenever we acquire a block of memory, we acquire a particular block within the confinements of that pool of memory. So that pool of memory is available for program use, and we obtain a block of memory from it. And in terms of what our representation will point to, elements will point to that, and capacity will point just past the allocated chunk of memory. Now here's the general idea. If we wanted to compute the capacity of the vector, to understand how many elements the vector can store without having to reallocate, then we perform the operation of pointer subtraction as follows. We do cap, perhaps write this outside, the capacity minus elem. And we are essentially to regard this pointer subtraction as obtaining the amount of memory stored between two particular memory addresses and then dividing that amount of memory by the size of the element type with which we are working. In this case, it's string. So in other words, this pointer subtraction essentially gives us the amount of memory located between those two addresses. And then we take that and divide it by the size of string, and in that way we can obtain the amount of elements that the vector can store. Now, in a manner analogous to that description, we are to regard this statement, pointer subtraction, as essentially giving this the amount of memory located between the first three pointer and elements, and then dividing that by, in this case, string. Note, I am quite frankly unaware of the details of pointer subtraction, but I would assume that it imposes, a constraint is imposed that whenever we subtract one pointer from another, the types of those pointers must be equivalent. In other words, they must both point as strings, for instance. In order for the implementation of the unit of computation that performs the actual work of evaluating what that operation is supposed to represent, essentially to enable that unit of computation to compute what the result should be. If the pointers had different types, then there would be no way to construct a reasonable result value. But anyways, that's irrelevant. It's not irrelevant, but it's not too important. The point is, this particular member function enables us to compute the size. Okay, let's get a move on here. Let's talk through this fast. Okay, so the next member function is capacity, and it works in a manner analogous to size. It returns an integral value. It's a const member function, the implications of which have been discussed in previous lessons, and it returns the result of subtracting the cap pointer in the representation, subtracting from the cap pointer in the representation the elements pointer in the representation. And that gives us the amount of objects that the vector can store without having to reallocate. We also define functions that return iterators to the first element and one past the last element, and we do that as follows. The begin member function, which is a const member function, will return elements, because elements is part of the representation that points to the first element of the vector. And then we have another member function returning a pointer to a string called end, which is a const member function. And it's going to return first free, because of course first free, as we will see as we implement this, points to one past the last constructed element. The next thing that we do is we have private access specification, and we have a static variable. In other words, this particular variable will be shared among all instances of the class type that we create. It's a static variable of type allocator, instantiated with string, called alloc. And this we're going to discuss. Of course, I would like to keep the lesson as brief as possible, but I thought it was important to go into a sufficient amount of detail relating to how allocate works, the allocator class works, and so consequently we will do that. But for the moment being, we are to regard this as the mechanism for acquiring memory and also freeing memory. That's what the allocator class represents in our particular implementation, and perhaps in general. Okay, so the next member function in the private access specification and the private access specification, defining these functions and the private access specification component of the class definition implies that not only can they be called by members of the class, but that's exactly what we're trying to achieve, because these utilities are only going to be used in the implementation of the various member functions. So there's no need to expose those implementation details in the public interface. So the next member function is a function returning no value called check_n_alloc, and it fairly simply performs the following test if the size of the vector is equivalent to the capacity we want to reallocate. And we will discuss the implementation of reallocate at some point in this lesson, of course. Okay, so next we define some more utilities. And the first one, the next member function, returns an object of type pair that stores two string pointers called alloc and copy. And its interface is specified in terms of pointer to constants of type string. It's a pointer to, so the interface is specified in terms of two string pointers, and the pointers in and of themselves are pointers to constant, meaning that we can't use the pointer to automatically change the value to which it refers. So that's how we specify the interface. And we will not actually proceed to implement this at this stage. Now we'll go through this very quickly. If I forget to mention what a particular member function does at any point in the lesson, just keep in mind that we will discuss it at length at some point, and so consequently it will be revealed what logical service it provides. But alloc and copy represents a mechanism for allocating a chunk of memory equivalent in size to the amount of memory located between the two pointers indicated by the parameters divided by the size of string. And then we copy into that allocated block of memory the elements denoted by the pointers that we passed. And then we return pointers into that allocated memory by means of the return statement that will essentially list initialize the pair. So let's go through this quickly. We have another function returning no value called free, and we've already detailed what that does. It essentially destroys the elements and frees the associated space with respect to the vector. We also have a function returning no value called reallocate, which will provide the logical service of reallocation. And now we discuss the representation. The representation consists of three string pointers The first one is called elements, which essentially points to the first element that the vector stores. The next is first free, which points to one past the last constructed element. And we will see that throughout this lesson when we begin to implement it. And the last is cap, which stands for capacity, and it points to one past the allocated chunk of memory. Also, I suppose I'll say this at this stage. In terms of built-in pointers, they provide the incrementation operator. And I'm not quite sure of this because I haven't done enough research into it in order to give a a good answer to this, or or to be able to explain it with a degree of accuracy. But in terms of how incrementation on pointers is implemented at the lowest levels of the system, it must take into consideration the type that the pointer can point to in order to be able to understand how far in memory we need to move the pointer. I think that's a reasonably justified inference, but I'm not sure. And that's the end of our definition. So we will just go over it very quickly. As you can see, this is the definition of the class. Okay. One second. Okay, so let's discuss the allocator class. The allocator class represents a mechanism for allocating chunks of unconstructed or raw memory. This is in contrast with the new operator, which combines the process of allocation and construction. This can be wasteful, as demonstrated by the following code. So let's write out some code to demonstrate the idea that the employment of the new operator can actually be quite wasteful in computational terms. Let me write this in a different color. Consider the following short code fragment. We declare an object, a pointer to an object of type string. It's a constant pointer called p, and we assign it the result of dynamically allocating an object of type string, in fact an array of strings of size n. Now suppose we declare another variable, this time of type string called s, and we employ the use of the while mechanism to provide repeated execution of a particular branch of statements. And we've already discussed the details of this kind of notation in the previous lessons. But essentially what we're going to do is we're going to read input from the standard input into the string representation, and then we're going to logical AND the result of that operation with the following check, which checks that q is not equal to p plus n. And if this in its totality evaluates to true, we apply the dereference operator to the postfix incrementation of q and assign it the value of s. Now there's a couple of things to understand here. First, this particular operator here is the logical AND operator, and it's one of the operators in C++ that guarantees the order of evaluation, because logically speaking, it combines two operands that can have value to a Boolean expression, and it only evaluates to true when both of those operands evaluate to true. And so as a consequence of that observation, if the left-hand operand evaluates to false, then that implicitly determines the result of the entire expression. And so consequently, it is redundant to check the right-hand operand. And so in that way, we do not proceed to check for q's equivalence or lack thereof with the value of p plus n unless the input operation was successful. And you know, in terms of what we're attempting to do here, we're attempting to read values into the string representation repeatedly until we have read as many strings as the array we dynamically allocated allows for. And the termination condition is essentially realized by means of the repeated incrementation of q in the loop body. And in terms of what this statement is doing, we're applying the postfix decrementation operator to q. And what that's going to do is it's going to increment the value of q, in this instance increment the pointer, and then return a reference to the old value. And then we dereference that and assign to it the value of s. And in that way, we can essentially assign values to the various different string objects located in the dynamic array. Now, the next thing that we do is we need to record how many strings we read, and we do that by means of the following declaration. We declare a constant integral type called size equal to q negative p, which is pointer subtraction, the implications of which have already been discussed. And the next thing that we do is that once we're done with that dynamically allocated array, we delete that dynamically allocated array by means of this notation. So, with respect to this particular code, there are two primary flaws in this particular code. The first thing is we may not need end strings, and so consequently we're allocating more memory than may necessarily be required. And the second point is that we construct those strings, which has a computational cost, and shortly after assign new values to these objects. So it's very wasteful, this particular implementation. Furthermore, classes that do not have a default constructor cannot be dynamically allocated as an array. This short example demonstrates that it becomes desirable to have a mechanism that enables us to allocate chunks of memory and only construct objects in that space when we need them and have suitable values for them. This is precisely what the allocator class offers. So, allocator is a class template parameterized on the type the allocator instance can allocate space for, thus enabling type-aware allocation of chunks of memory. Okay, so we use the following notation to create an allocator that can allocate space for strings. To declare an object of type allocator, instantiate it with string called alloc. Now, the following program and code fragment will demonstrate the interface provided by the allocator class and the various operations that it provides. So, taking into consideration this declaration, what we can do is we can declare a variable called p, which is a constant. In this instance, it's going to be a constant pointer because in terms of with respect to the initializer, the type automatically deduced, which is something that's done when we use the auto type specifier, will be a pointer type. And we apply const to that, we get a pointer to a constant. A constant pointer, excuse me. So we assign that the result of calling the allocate member on the alloc instance, passing to the interface n. And that's essentially going to allocate memory for n strings. Again, this is just a sample program to demonstrate the interface and the operations provided by the allocator class. We declare a variable called q, initialized with p. And we do this because we wish to construct elements in the space allocated by the call to the allocate member function here. But we do not wish to lose access to the first element in that dynamically allocated, what is essentially a dynamically allocated array. And here's what we can do. Consider the following. We call the construct member function on the alloc instance, passing to the interface the postfix decrementation of q. We then do this again, and again what we're doing here, and we will discuss this in detail after, is we are constructing elements in the space allocated by the allocator. So we pass the postfix incrementation of q, and then we pass the value 10 and the char and the value c, which is a char value. And we do this once again. Let me just make these larger so we can tell it's member selection, member access. We call the construct member function again, and the first argument we pass is the postfix incrementation of q, and then we pass the string literal high. Now the construct member function constructs an object at the location specified by the pointer specified as the first argument, which must be a pointer returned by a call to allocate, and does so in accordance with the constructor corresponding to the extra arguments provided. Now observe the following. We're passing different amounts of arguments. And so this would seem to imply that the constructor is overloaded. But overloading the construct member function would be impractical because there would be no reasonable way to provide overloads that correspond to every conceivable constructor that could ever exist. That would be, of course, absurd to expect. And so consequently, it isn't implemented in terms of various different overloads, it's implemented as a variadic template. And the variadic template essentially is a mechanism for accepting an arbitrary amount of types of differing an arbitrary amount of objects of different types. Okay, the next thing that we do is we employ the use of the while loop, and we check that q is not equal to p. And so long as that is the case, we call the destroy member function, and we already alluded to as to what this represents previously. On the prefix decrementation of q, and after doing that, we call deallocate, the deallocate member function on the allocator instance, passing to the interface p and n. Now in terms of what we're attempting to achieve in this particular segment, we're essentially attempting to run the destructor on each constructed object. And in this case, we obtain the last constructed object by means of postfix decrementation of q, and we do that repeatedly until q is equivalent to p, indicating that we have run the destructor on every constructed object. And as a consequence of postfix decrementation, this will not underflow in terms of the logic of how it works. And in terms of what this particular expression does, it essentially gives memory back to the system. And you have to note that the pointer passed to deallocate must be a pointer previously returned by a call to allocate, and the value n must be the size of the dynamic array that we allocate. In other words, the amount of objects that that chunk of memory associated with that pointer can store. Because otherwise, we would essentially lose reference to, if we passed a value less than, in fact I'm not quite sure how it's implemented, but the presumption is that at the most basic level, if we passed a value less than the amount of objects allocated in dynamic memory on the free store, then we would essentially lose reference to it in practice, in effect. Okay, let's move on. One second. Okay, so let's actually move on to start to implement the various different members indicated by the class definition. And the first is the operation of pushback. And pushback provides the operation of adding an object to the vector. So let's go through this quickly because it's a relatively simple example today. I don't think we need to spend too much time explaining this. So we're defining a member function within the context of StrVec called pushback, the interface of which is a constant reference to an object of type string called S. And the first thing that we do is we call check n_alloc, which essentially checks if there's enough space for an extra element, and if not, causes reallocation to take place. And in either case, we call the construct member function on the allocator, which is statically allocated, passing the postfix decrementation of first free, and we need to postfix increment that, and s. So when using allocator, memory is unconstructed. Consequently, one second. Okay, so when using allocator, memory is unconstructed. Consequently, we use the construct member function in order to construct objects in that memory. The first point to note is that the first pointer must be a pointer to unconstructed space obtained by a call to allocate, and the remaining arguments determine the constructor that will be used to construct the object that goes in that space. In this case, we're passing a string, meaning that we're going to invoke the string copy constructor. Now, in terms of what we're doing here with respect to the implementation of first free is going to initially point to the first location in the dynamically allocated chunk of memory that we can construct a string in. But we also want to provide the service of incrementing the first free pointer such that it points to the next available location. And to be succinct and to be concise about it, we essentially apply the postfix incrementation operator and return a reference that returns a reference to the initial value first free, but at the same time increments first free. We could, in theory, do those in separate instructions, but we don't do that for the sake of brevity, I think is the word. And that's all that it does. Now, it's using a utility function to do the work that it does. Okay, so the next thing that we're going to discuss is the alloc n copy member. So let us implement that as follows. Recall that it returns a pair of string pointers, in essence, and the reason for that will become clear as we discuss this implementation. And we need to access the context of StrVec. The member function is called alloc_n_copy, and it has an interface specified in terms of constant references to pointers to objects of type string. And the first parameter we call b, and the second parameter we will call e. And I suppose this will become clear as we move through this implementation as the lesson goes on, but essentially that denotes a range of elements. And so that's why we use the letters B to indicate begin or beginning, and E to indicate end or to indicate end. Now the implementation looks as follows. We declare a variable by using the auto-type deduction specification mechanism called data, initialized with a return value of calling the allocate member function, which will allocate a dynamic chunk of memory or a dynamic array equal to the size with respect to the amount of objects it can hold to E-B. In other words, we want to allocate enough memory to store the amount of elements denoted by the iterator range BE, which is a half-open range. which is essentially going to be a half-open range in practical terms. And fairly simply, we have a return statement that list initializes the pair that we return with data. And again, data will be the pointer to the first location. Essentially, data will be we can't say it's going to be the pointer to the first element because we haven't constructed the element. But what we would say is that data points to the starting location of the dynamically allocated block of memory. And the next thing that we do is we call a function called uninitialized copy, passing to the interface B, E, and data. So this particular function is called when copying or assigning a StrVec to provide value-like behavior, which is to say that subsequent modification of a target does not in any way affect the source. We allocate sufficient memory to store the elements represented by the source and copy the elements from the source into this newly allocated space. And we do the latter part of that statement by means of the call to uninitialized copy. Now let us actually discuss what uninitialized copy is, and I will do this by quoting directly from the book from which the example comes. So uninitialized copy. Let's specify its notation that indicates its use down here. So suppose we wrote uninitialized copy, and we have B, E, and B2. Essentially what this does is it copies elements from the input range denoted by iterators B and E into unconstructed raw memory denoted by iterator B2. The memory denoted by B2 must be large enough to hold a copy of the elements in the input range, and also the iterator must refer to raw unconstructed memory. An uninitialized copy is essentially a utility function used in conjunction with the allocator mechanism. Okay, so let's move on to discuss the implementation of free. We have a function returning no value. We need to access the context of StrVec called free with no parameters. And the implementation does the following. We check if we have an if statement, the target of which is elements, which is a pointer, which provides an implicit conversion to type bool. And in that case, if it's null, if it represents the null pointer, it will automatically convert to false in terms of its Boolean value, and otherwise it will return true. So essentially we're checking if elements points to an object in memory or if it doesn't. And if the test succeeds, essentially what we have to do, we will do, in fact, one second. So essentially what we're doing here is free is supposed to provide the service of freeing the memory associated with a vector. And that is done in various contexts for different reasons. And in order to achieve that objective, we have to implement the algorithm that does the necessary steps to create a program that is logically sound and reasonable. And so the first thing that we do is we employ a for loop, the initialization portion of which declares a variable called p initialized with first free. And in terms of our implementation, assuming no ingenious hacking, the elements beyond the addresses beyond first free within the confinements of the allocated block of memory will not contain any constructed elements. And so consequently, we can proceed as follows. The test checks that P is not equal to elements, and we don't do anything in the action portion because we automate that in the implementation of the body. We don't need to specify curly brackets. So the body very simply calls the destroy member function on the postfix decrementation of P, which will run the destructor on the object to which P points. Now, once we've run the destructor on each element that was constructed, we can then deallocate the memory by means of a call to deallocate, passing to the interface elements, which points to the initial location of the block of memory we dynamically allocated, and the integral result of applying subtraction to these two pointers, which essentially gives us the amount of memory that was allocated. And that's the end of the implementation. So the first thing to note is that we need to destroy the elements, and then we need to deallocate the space, and also the pointer passed to deallocate must be one previously returned by a call to allocate. Okay. Given the preceding definitions, we can implement the copy control members as follows. So let us proceed to implement the copy control members. And we will do this very quickly in the interest of time. The first thing we do is we define the copy constructor as follows. The parameter, of course, is a constant reference to an object of type StrVec. And the algorithm that we implement does the following. We declare a variable called new data, initialized from the result of calling alloc and copy passing to the interface the result of calling the begin member function on the S instance and the end member function on the S instance. In other words, essentially what we're trying to do here is to copy construct the StrVec, we need to allocate memory and copy. We essentially want to have a situation whereby we have another StrVec that is in some sense equivalent to the initial, to the source of the copy operation. And so to do that, we need to allocate an amount of memory in equal measure with respect to the amount of memory allocated for, or the amount of memory necessary to store the range of elements in the source of the operation, the copy operation, and then we need to copy all those elements from the pre-existing memory into this newly allocated chunk of memory, and the allocate copy, as indicated by the previous implementation, performs that action for us. Second. Okay. Now the next thing that we do is that we set elements equal to the first data member of new data, and we know what that represents. It represents the location, the starting location of the dynamically allocated block, and we need elements to point to the initial element we constructed in that space, and we do that by means of this particular assignment here. And we then assign to first free and cap the data member second of new data, which is a pair, as we indicated before. One second till I write something down, just so oh, I'm gonna have to get up. I could drop my pen. One second, there will be no time at all. One second. Okay, so anyways, we assign to capacity. One second till I write this down. So we assign to capacity and first free the second member of the new data pair, and this represents the idea that the second member will correspond to one past the last constructed element, and so in that case we have to assign it to first free because first free represents that, but we have to observe that we only allocated enough memory to store the range of elements denoted by the iterator range, and so in that case the capacity will be equivalent to first free, which is first free will be equivalent. Capacity will be equivalent to the second data member, and first free will be equivalent to capacity, or cap for short. And that's the end of our implementation. Now let's implement the destructor, which is a relatively trivial task. We can do it here. Oh yeah, we can do it here. So the destructor is as follows. We access the context of StrVec. It's the destructor by means of that, indicated by means of that token. And the implementation fairly simply called free, and we've already indicated what that does. This is one of the contexts that free is called in, and it's going to free the memory managed by a particular instance of the class type. Okay, so the next thing that we're going to do is we're going to implement the copy assignment operator. And that can be done as follows. It returns a reference to an StrVec, in this case the implicit this parameter, to adhere to the convention that we wrote on the left-hand operand of assignment operators. We need to access the context of StrVec, and we're defining the assignment operator, where the source of the assignment operator is an instance of type StrVec. One second to check something. Okay. So essentially what we do here is the algorithm that we're going to implement is we declare a variable of type data initialized from calling alloc ncopy passing to the interface on the result of calling the begin member function on the RHS parameter and the end member function on the RHS parameter. And in this case, in this instance, and again, before I continue, with respect to devising logical structure, that relates to devising a series of statements that constitute an algorithm. So essentially we have this notion of what we want to provide in terms of a facility. And we have to implement the appropriate algorithms that can provide the behavior that we require. And so we need to implement an algorithm that enables us to essentially copy assign an object of type StrVec. And in this case, we can observe relatively clearly that we want the element stored in the source of the vector to be equivalent in the target of the assignment. Let me rephrase that. We want the element stored in the target vector to be equivalent for the source vector, or perhaps it would be more appropriate to say that the other way around. We want the element stored in the source to be equivalent to the element stored in the target. And so consequently we need the alloc n copy member function provides that service of allocating a chunk of memory and copying all the elements into that memory. The elements stored within the RHS parameter, and then we return a pointer to the start of that allocated, to the first element of that particular block of memory. Then we call free. Note the order we do this, and that is to protect against self-assignment. And we have to call free to free the resources obtained previously so as to prevent a resource leak, because we subsequently do the following. We assign to elements, the elements data member, data.first, and again data is going to be a pair because alloc copy returns a pair, and we return first, we assign to first free and cap in a manner analogous to our previous copy constructor the second data member of data, and then we return the thing to which the implicit this parameter refers. One second. Okay, I was going to mention a point there, but I forget what it was. So we will just move on, and perhaps it will occur to me at some point. So next, the next thing we will do is this. Next, we will implement the reallocate member. In accordance with the principles set forth in lesson 2, we carefully consider precisely what the function must do and in what order in order to achieve some desired logical objective. When we do so, we construct the following algorithm. The first step, allocate memory for a larger array of objects. The second step, construct the first portion of this memory to hold the pre-existing elements. And the last step is to destroy and deallocate. In other words, free the pre-existing memory. The pre-existing memory that was allocated. Our task is to then identify the appropriate language and library facilities that can implement the behavior required by this specification. Now here's something that's quite important to understand. As a consequence of and we're going to draw some diagrams here. As a consequence of the observed induced ephemeral nature of the pre-existing strings, we can implement an important optimization. We should move the strings, not copy them. And so let's draw some diagrams to indicate what copying means. Suppose we abstractly had the following statement. We had two strings and we assigned the S2 string to S1. How can we represent that in terms of a diagram? Well, we can represent it as follows. S2, we don't know how string is implemented, but essentially, in its representation, it points to a dynamically allocated array of chars. And so, In this particular statement, this is going to result in a situation whereby S1 and its representation will point to a dynamically allocated array of chars that is equivalent to this particular dynamically allocated array of chars here. Now that's the semantics of a copy operation, and it produces the notion of object independence. But suppose in the abstract sense, not saying that this is valid code, nor am I implying it, but suppose that we said something equivalent to the following. And we will discuss what move does within this lesson. Using this notation, it's going to invoke the move constructor. And in terms of how we can represent the operation of the move constructor, we essentially have a situation whereby the S2 representation points to a dynamically allocated array of chars, and S1's representation will point to that same dynamically allocated array of chars, and after that, S2's representation will point to nothing. And as you can see, as indicated by this this left-hand side diagram, the normal copy operation implies allocating enough memory and calling the copy constructor for the element type. That's quite an expensive operation relative to this particular procedure here, whereby we simply steal the representation of a particular source object, and that operation is as efficient as a simple pointer assignment, and that's all that it takes. So we can implement the reallocate member and discuss it at length. So let's proceed to do just that. One second. Okay, 1 second, I'm just looking over something. Okay, so in accordance, we're going to discuss this at length. So let's proceed to discuss the implementation of reallocate. And again, this reallocate member function will represent the strategy that we employ when it comes to actually reallocation. And in terms of our strategy, the first what is essentially an instruction, will essentially encode our particular implementation strategy with respect to vector growth. So let's proceed to implement reallocate as follows. So we have a function returning no value. It's a member function. We access the context of StrVec called reallocate. And the first thing that we do is we declare a variable called new capacity equal to the following. Okay, so in terms of what we're doing here, this variable represents the new capacity. In other words, in terms of our implementation strategy and with respect to vector growth, every time we reallocate, we want to allocate more memory than is required to hold the pre-existing element and the element we're trying to add. And so consequently, we need to compute a value that represents the new capacity that we're going to, the new capacity of the vector. And in our particular implementation of reallocate, essentially what we do is we use the conditional operator, and the conditional operator essentially checks the return value of size. The return value of size is an integral value which is implicitly convertible to bool, and so consequently if size returns 0, if size returns 0, it will select this option here, and thus it will assign to new capacity the value of 1. Otherwise, if size is a non-zero value, then this evaluates to this particular option is chosen such that the result of the conditional operator is the result of multiplying the size by 2. And so implicit in this very instruction is our particular implementation strategy for vector growth, which is that we double the capacity every time we reallocate, unless in the specific case we haven't actually added any elements to the vector, in which case we simply start at 1. And a consequence of this is that it will always be multiples. It will always the capacity will always be 2 to the n, where n is some specified number. Okay, let's proceed to implement the next instruction. So the next thing that we do is we allocate. So we declare a variable called new data, and we essentially allocate memory for an amount of objects equivalent to the integral value new capacity. Okay, so the next thing we need to do is we need to actually duplicate. So in other words, what we're doing in the statement is we're dynamically allocating an array, dynamically allocating a block of memory able to store new capacity strings. So the next thing that we need to do is we need to declare a variable that records the value of new data, because we don't want to update the value of new data, but we'll need to iterate over the memory addresses starting at that particular location. So consequently, we duplicate that by means of the following initialization. And what we do is we obtain a pointer to the first element in the old array by means of the following initialization. Again, elements points to the first object constructed in the space managed by the vector. And so here's what we do. We've essentially dynamically allocated this memory, and we need to move all those objects from the old memory to the new memory. And so we do that by means of the following for loop. The initialization portion declares a variable of an integral type called I initialized to 0. We check for i's inequality with the result of calling size. And one thing you have to understand here is that the size member function is being invoked on the implicit this parameter. So it's the size on the vector that we're attempting to update or reallocate. The amount of objects that it stores. And then in the action portion, we increment I. Now in the body, what we do is as follows. We call a construct member function to construct an element in the space we previously allocated. And this is where desc comes in. We apply the postfix incrementation operator to enable construction in the appropriate region of the memory allocated, but also to avoid having to increment it in the action portion of the for loop. And so we're constructing an element in the space that we just dynamically allocated. And what we do is as follows. we pass the result of calling move on the postfix incrementation of elem dereferenced. Now what's going on here? Well, firstly, this particular argument corresponds to the constructor that will be invoked to construct the element in the unconstructed memory. And if we analyze the technical specifications of this, move is essentially going to return some value, presumably in accordance with the argument that we passed. Now, what we are doing is we are applying the postfix incrementation operator to elem and returning a reference to the old element, the old value of elem, and dereferencing that. That's going to essentially give us the value, the first value stored in the current vector representation in terms of the memory that it initially managed. And so we're essentially going to obtain a reference to the first object that was constructed in the pre-existing memory. And so in this case, it's going to be an object of type string. And what we do is we call the moveMember function, passing to that an object of type string. And in that case, it's going to return an R-value reference to that object, such that the argument that we're passing, because we have to evaluate the result of calling the function, the argument we pass to construct is an R-value reference to a string. And because it's an R-value reference to a string, it's implicitly going to invoke the move constructor to construct the element directly in the memory that we allocated. Thus, instead of copying by means of a copy constructor, which is a relatively expensive operation compared to moving, we simply move by stealing the representation of the old string to the string that we're constructing in the space that we dynamically allocated. Okay, so the next thing that we do is we call free. One second. We call free to deallocate the pre-existing memory, and then we update the representation appropriately. We assign to elements new data. Now in this instance, first free and capacity are not going to be equivalent. And so we assign to first free the result of dest, which has been suitably incremented to the point whereby it refers to one past the last constructed element. And we assign to cap, or capacity, the result of elements plus new capacity. Now, of course, in this particular case, elements points to the... we could graph this out. We have this dynamically allocated chunk of memory, and elements points to the first location. And whenever we have a situation whereby we have pointer addition defined in terms of an operand that's a pointer and one that's an integral operand, that's going to yield a pointer to that many elements along in accordance with the type to which the pointer points, such that we essentially obtain a pointer pointing to one past the last location allocated by the call to the allocate member function, such that capacity points to essentially will point to one past the allocated memory, which is exactly what we want. And then that's the end of our implementation. So essentially what we have done here is we have constructed an algorithm that is logically reasonable and sound, that gives us the semantics of reallocation. Okay, one second. So that's our reallocate member function. So the next thing that we're going to do is we're actually going to implement a move constructor. One second. Okay, so the next thing we're going to do is we're going to implement the move constructor. So let's do that now. So we can do it as follows. We're defining a constructor that is the move constructor, and we apply this no except specification, and we will describe the purpose of this momentarily. It essentially specifies that the function implementation won't throw any exceptions, although that isn't enforced by the compiler. In fact, we need a constructor initializer list. We set elements, and again, okay, let's discuss what it's doing first. We set elements to s.elements. First free to s.first free, and capacity equivalent to s.capacity or cap. And the implementation sets the representation of s to indicate that it doesn't point to any, it essentially doesn't point to any allocated memory. It essentially represents an invalid container. Okay, so what is it we're trying to do here? Essentially, the move constructor is a mechanism for stealing the represent. Instead of, if you allocate a chunk of memory and you want to copy, if you allocated a chunk of, if a class type acts as a handle to a dynamically allocated chunk of memory, and it stores a series of objects of some specified type, and you wanted to copy that object into another object, then adhering to normal copy semantics would essentially dictate that you have to allocate an amount of memory equivalent to that pre-existing block of memory in terms of its size, and then use the copy constructor of the element type stored at that particular, of the data type stored at that particular, in that particular block of memory, to copy each element from the old memory to the new memory. And in that way, we obtain a situation whereby we essentially have two objects that are, in practical terms, essentially to be regarded as being equivalent. But that's quite an inefficient operation, especially with respect to something like a move constructor. So the move constructor essentially steals the pointer values, or the representation, from some source object, so instead of having to dynamically allocate another chunk of memory and do all those copy operations, you essentially just say, take the target of the copy operation and make it point to that dynamically allocated chunk of memory, and update the representation of the source suitably. So in relation to that, the move constructor must ensure that the move from object is left in a state such that destroying it is logically reasonable. In other words, if we didn't assign null PTR to each, and by the way, we check before attempting to run the destructors on the elements let me just check this. In the free data member, we check that elements is not null, and so in this case it is null, and so consequently we will not execute that particular branch of code. But if we didn't update the representation, then the destructor would be invoked, and in that case, it would free memory associate. It would essentially run the destructors in free memory associated uh, with a particular region of memory, uh, which is pointed to by the target of our copy operation. So the move constructor represents an efficient mechanism for copying a value. So I'll just indicate this. The original object must not point to the resources, and that's as a consequence of the implementation of the destructor, because responsibility has been moved to another class instance. Okay, so what about this noExcept specification? We specify noExcept to ensure that the move constructor is used when we reallocate a vector. In other words, if we want to use a vector whose elements types are our particular container, which is StrVec, and we want it to be done in the most optimized way possible, we specify noExcept. So this is with respect to the implementation of the standard library vector. This is a way to inform the library that our move constructor does not throw. In this way, the vector implementation will use the move constructor rather than the copy constructor during reallocation, because they can provide the guarantee that the vector is left unchanged if an exception is thrown, which will not be which will not of which of course will not happen with noExcept specifications. It's not enforced by the compiler, technically speaking, though. If it used the move constructor and it threw, we would have a situation where we modified some of the initial elements and not others, and before we could update the representation, program execution automatically went to an error handler, which deals with the error, and program execution continued. This problem does not exist with copy constructors, given this name as a consequence of their signature, that adhere to the semantics of object independence. So the next thing we're going to do is we're going to implement the move assignment operator, which essentially operates in an analogous way. And in terms of how assignment operators are implemented, they usually combine the functions of the destructor and the copy and the copy constructor. So let us proceed to implement move assignment. One second, let me just write something down just so that I cover it towards the end, so I don't forget about it. So let's implement the move assignment operator. And we will do it as follows. It returns a reference to an StrVec. We're entering the context of the StrVec definition, and we're overloading the assignment operator in a context whereby, and again, I should say this. In fact, I'll write this out. Okay, I'll write it here. This is a good place to write it. We have to assume the following declarations within StrVec. So our implementation of the definition is equivalent to what it was, but we extend it to include the following declarations. First, StrVec, a constructor, essentially the declaration corresponding to the move constructor. And we have to specify noExcept on every declaration of that function. And we would also have to now, our assignment operator is a member function. Of course, the move assignment operator. And its prototype looks as follows. do we specify no except? We'll not specify no except. So we need those declarations and other members as before. Okay, so we need to extend the definition to include those declarations. The move assignment operator. In fact, we do specify no except. Let's just do that quickly. Suppose that wasn't there. No except, like so. Okay, so let's proceed to implement the move assignment operator. So it's used in the context whereby we supply an R value of type of type StrVec as the right-hand operand to the assignment operator. And the implementation does the following. First, we have a direct test for self-assignment. And in some respects, this can be more efficient in certain for instance, this is a simple comparison of two pointer values, and we then implicitly convert the result of that to bool. But if we devised even a copy constructor such that, logically speaking, it made sense for self-assignment but caused unnecessary memory allocation, that could perhaps be quite costly. Now, on the other hand, if we always used the copy constructor in the appropriate manner, that is to say, if we never done self-assignment, then this pointer comparison would be one extra unnecessary step. And so really it's just a question of determining, do you want simplicity in implementing it without having to devise your logic to take into consideration self-assignment, or do you want to be more efficient with the extra burden of increased complexity? So if this evaluates to true, in other words, if we're not self-assigning, then do the following. Call free, and we can do this because the vectors essentially point to different locations in memory. We then assign two elements, the elements component of RHS, we assign to first free the first free component of RHS. In other words, we're stealing its representation in a way analogous to the move constructor. And we set capacity, or cap, equal to the cap component of RHS. And the next thing we need to do is we need to leave RHS in a state that is reasonable in terms of a state that makes sense with respect to destructor invocation. And we do that by means of the following assignments. Essentially, we're assigning to the representation the null pointer value. And of course, we don't have much space here, so we'll just write this here. We then return the thing to which the implicit this parameter refers. And that's the end of our implementation. So that's the implementation of the move assignment operator. In fact, we did have room, it doesn't matter. So, I suppose one thing that we need to take into consideration is that the direct test for self-assignment would seem to be redundant given the fact that the parameter is an all-value reference, but this is because the result, RHS, can be the result of calling std move on that particular object to which we're assigning. Uh, and also, we must adhere to the general principle that we don't free LHS before using RHS. In other words, if we freed the memory associated with the vector to which we are assigning, and the right-hand operand of the assignment operator was that very same object, then in that case, we would have a situation whereby it wouldn't be logically reasonable. Because we freed the memory, and so consequently RHS doesn't point to any memory. In fact, in terms of the implementation, it's probably going to cause a program crash, because it points to invalid locations in memory in terms of its representation. Okay. Okay, so let's move on to discuss the following. 1 second. We're going to discuss an alternative way to implement reallocate. And we're going to do it as follows. One second. So we're going to extend our implementation. We're going to propose an alternative implementation of reallocate that uses initialized copy. And before we can proceed, we essentially have to write out what in some sense could be regarded as pseudocode, an implementation of the uninitialized copy function. And we can regard it as being analogous to the following code. Let's change the color. So a simple implementation of the uninitialized copy member function, or the uninitialized copy function, which is designed to construct objects in raw memory, which will be indicated by the implementation, can be as follows. It is a template with a type parameter called capital X and a type parameter. In fact, should we simplify this? Okay, let's simplify it. Okay, it's got a single template type parameter, and we'll use the notation u_c for the sake of to be succinct. And the parameters are the type digit for X, and one's called B, one's called E, and one's called F. And the implementation can be regarded as follows. Essentially, we have a using a declaration to associate the string type with a type obtained by means of the following notation. And we will see why this is necessary in a moment. Now, in terms of what's going on here, essentially what we need to do is the X type is essentially an iterator type, and we need to create an allocator that can allocate objects to which the iterator refers. But we couldn't declare the allocator in terms of the template type parameter, because of course that would mean that it would allocate objects of a pointer type or iterator type, and that's not what we want. We want the type to which the iterator refers or can refer to. And so consequently we need some mechanism to extract that information. Now, I know not the inception of the template mechanism nor its motivations, But one thing is clear, and it is as follows. What is perhaps an unintended consequence of the template mechanism, in terms of how it actually functions, is the idea that we can essentially extract information from data types that are composed from various different other symbols and so on, and in that way extract critical information from it. And so this, I think, it's essentially a type trait. And so what we're doing here is we're passing, we could essentially regard extract type from PTR as a type trait with a specialization where the template type parameter is a pointer to some unspecified type, and we capture the type to which it points in the template type parameter, and then devise a using declaration within its context that refers to the type of the template type parameter in the form of the type component of the implementation. And in that way we can obtain the type to which the iterator refers. And that's going to be necessary for the following declaration. So we declare an allocator that can allocate objects of type called A. We then say while B is not equal to E, A.construct, while B is not equal to E, call the construct member function on the allocator A, passing to it the postfix incrementation of F dereferenced and the postfix incrementation of B dereferenced. And that's the end of the implementation. In other words, in accordance with the definition we gave for uninitialized copy, with respect to the semantics of the third parameter, F essentially represents the destination to which we need to write the elements. And that destination must refer to raw memory. And so in this case, essentially F represents the first location in that dynamically allocated unconstructed memory. And so consequently, we essentially dereference it to obtain access to that first location. Actually, 1 second, let me just check something. No, that's wrong. We don't dereference. That's a mistake. 1 second, I will rub that out momentarily. We don't dereference that, but we do dereference the postfix incrementation of B. So we essentially pass the pointer F, which corresponds to the first location in the unconstructed memory, and in that particular memory location, we construct an object in accordance with the type with which the allocator was allocated, using a constructor that accepts an object of the type that the dereference operator on the B iterator yields. And in this case, that's going to yield some constructor. So that's the a simple implementation of an uninitialized copy. Now here's the key point. So essentially, we can regard the implementation of an uninitialized copy as follows, as being analogous to that. Observe, however, that if we modify the behavior of the dereference operator to return an R-value reference to an object type, then we can cause the implementation of uninitialized copy to implicitly invoke the move constructor. In other words, if we adapted the dereference operator such that, when applied to the iterator type, returned an R-value reference to an object type, then that would implicitly invoke the move constructor in the call to construct. And that's precisely what we want. So what we're doing is we're attempting to redefine the reallocate routine in terms of a call to an uninitialized copy, whilst preserving the important optimizations that we introduced in the implementation of reallocate that uses a more conventional looping structure. And so the question is, how do we change the behavior of an iterator's dereference operator such that it yields an R-value reference to the type to which it refers? And we can do that by means of by introducing the notion of move iterators, and in particular a move iterator adapter. And what it does is it adapts the behavior of the dereference operator for a particular iterator type. And so in order to transform an iterator, we transform an iterator by calling the library makeMove iterator. And so consequently, we can implement reallocate as follows. So let's implement reallocate in terms of a call to uninitialized copy. So we can implement reallocate as follows. It's a function returning no value, member function returning no value within the context of StrVec called reallocate. And we declare a variable called new capacity, which is the same logical role as we initially described. That's not how you spell capacity. And we declare another variable called first that points to a dynamically allocated block of memory obtained by a call to allocate on the statically allocated allocator object, equal in size to the integral value of new capacity. Now here's where we define it in terms of a call to uninitialized copy. We essentially, again, the return value of uninitialized copy defined returns the return value of uninitialized copy is essentially an iterator denoting one past the last constructed element. And we assign that to a variable called last. We use auto-type deduction mechanism. The auto-type deduction mechanism, we already discussed what that means in the previous lesson. And so if you need to understand that, just go to that lesson number 2. And we assign it the result of calling uninitialized copy and what we do is we pass the result of calling makeMove iterator, passing to the interface the result of calling the begin member function on the implicit this parameter. And we do the same thing for the next argument. But this time we call end. And then we pass first. Okay, so essentially what we're doing here is we're obtaining an iterator denoting the first and one past the last elements in the... In fact, is it necessary to call makeMove iterator on end? It must be, because okay, that would seem to imply that the template there isn't 2 or 3 template type parameters. There's a single template type parameter that describes the type of the input range. So consequently, we do have to call makeMove iterator for a second time. But essentially, the call to begin and end returns iterators of some specified type, and we need to adapt that iterator such that the dereference operator has the behavior. Okay, so what we're doing is we need to essentially adapt the behavior of the dereference operator such that it returns an R-value reference to the object to which the iterator refers, and we can do that by a call to makeMove iterator. I would essentially regard it as being an abstraction. We'll not discuss how it could theoretically be implemented at this stage. It's an abstraction that makes programming more productive. Now, to finish off our implementation, we call the free function to free the existing memory. We initialize elements, or we assign to elements first, which points to the first object in the allocated memory. We assign to first free, of course, the result of last, which is the return value of the uninitialized copy function. And we assign to capacity, or cap, the result of elements plus new capacity. And the logical foundations for that were already discussed in our initial implementation of reallocate. So it's as simple as that. We have implemented reallocate in terms of a call to uninitialized copy, meaning that we don't necessarily have to employ the use of a conventional looping structure to achieve the same desired effect. Okay, 1 second. One second, I'm just checking something. Okay, so to end our vector implementation, which is a relatively simple implementation, we'll develop a more sophisticated example whenever we discuss further implementations of vector. But to end our vector implementation, we will provide a final operation called emplaceback, whose job is to construct elements by means of a constructor in the space managed by the container. And so before we do that, I would like to walk through the following example. Let me just make more space. Okay, let's okay, so consider the following. Suppose we have a template with a single template type parameter called x, a function template whose parameter is an R-value reference to a template type parameter called small x, and the implementation calls a global function, or a global calls the member function construct on a global variable. And again, some people say that the use of global variables is per programming practice. I think that's what they say. But if there's certain logical constraints imposed on the program by means of its very structure, then global variables can, in some sense, be a useful way to overcome those constraints. But essentially, we call a construct member function on a global allocator object, and we pass some unspecified but nevertheless valid global pointer that points to raw memory. And the next argument we pass to construct is the result of calling forward, which is instantiated with x, called with sub x or small x. Okay, so just consider the following. If we pass an R value of type int to this particular implementation, then the type deduced for t will be int. When we apply forward to this type, it will produce an r value reference to int. However, if we pass an L value to a parameter that is an R value reference to a template type parameter, the type deduced for t will be an int reference. When we apply this type to forward, it will indirectly create a reference to a reference. As a consequence, reference collapsing rules come into effect, and in this case forms a normal L value reference. In this way, we preserve the L valueness of an argument, or the original type information of an argument, such that when we invoke a constructor, it will invoke the appropriate version in accordance with the type of the initial argument. For instance, for an R value of the type of the argument we are constructing, the move constructor is invoked. So in other words, what I'm saying here is forward is predicated on the employment of an R value reference to a template type parameter. Now, if you don't understand what I was just talking about, that's fine. Just comment below and I will help you out with it. I was going to go into a detailed discussion of how forward is implemented and so on, and reference collapsing. But for the sake of simplicity and for the sake of conciseness, I thought that would be too time consuming. So consequently, I just thought I would articulate some key ideas in relation to it. And then implement it quickly. So let's actually proceed to implement this. One second. Okay, one second, I'm just reviewing something. One moment, I will be no time at all. Just reviewing something. Okay, so let's begin to implement the appropriate code. So the first thing we need to do to extend this to provide the InPlaceBack member function, we need to add to the definition of StrVec in the public access specification section the declaration of a function which is a member template with a single template parameter, which is a variadic parameter called args, and we will discuss what that means shortly, returning no value called InPlaceBack, InPlace_back, with a set of parameters that are essentially R value references to the corresponding type that is passed. And in order to reason about the behavior of this when we pass an L value reference, we basically just invoke the notion of a single template type parameter with a parameter of the function template that is an R-value reference to a template type parameter. Essentially, the behavior is the same. The only thing that's changed is that we're enabling a mechanism to pass an arbitrary amount of objects of differing types. Now this function parameter pack is called args. No, we don't have to name this, so just disregard that. We could name it if we wanted to. And then we have members as before. And then we close our definition. Now let's actually proceed to implement this member template. So of course it is a template, and class and type name are equivalent. There's no difference in using them. So we have a variadic parameter, a variadic template parameter called args. We specify it as inline, the implications of which was discussed in the previous section. It returns no value. We need to access the context of StrVec. The member function is called InPlaceBack. And its parameter is essentially an R-value reference to a type, some specified type or unspecified type at this stage. The parameter is a function parameter pack where all the elements are R-value references to some unspecified type at this stage. Okay, so let's actually implement what this function does. So the first thing that we do is we call check n alloc to ensure that there's enough space to add another element to the vector. And once we do that, there's only one more statement that we need to introduce, and that is a call to the construct member function that constructs an element in the memory referred to by the first free data member and suitably increments it using postfix increment notation. And the next thing that we do is we pass the result of calling forward, which is a function template, and we explicitly specify the template parameter. But in this case, we're going to use pack expansion, and we call it with some specified argument, which is an object, an instance of a class type. And we apply the pack expansion notation in order to cause there to be pack expansion. And that's the end of our implementation. Now, we're going to describe in detail what's actually going on here. So we've already discussed the reason about this code. All we have to do is consider what would happen, as we did before, in the case of a single template type parameter with an interface specified as an R-value reference to that template type parameter. In that particular case, it can be bound to any kind of argument, and the type deduced for t will be indicative of the L-value R-value property of the argument we supplied. Now, in order to forward an object passed to the interface with its type unchanged with respect to the original argument, it is necessary to use forward, which essentially returns an R-value reference to its argument. And it's predicated on the idea that args will be a reference type if it's an L value, and it will be a normal data type otherwise, such that forward returns an R-value reference to its argument type, and reference collapsing rules come into effect such that we have a situation whereby we will either return an R-value reference to an object type or an L value reference to an object type, and that in turn will then cause there to be the invocation of the appropriate implementation, such that if we wanted to forward an argument and have a move constructor called, then if we pass an R value, that's the result that we'll get. So let's analyze in particular what's going on in relation to this. It's a pack expansion. I will just enlarge these dots to make sure that that is clear. It's a pack expansion. So what's going on there? So we have this pack expansion. Args is a parameter pack that essentially contains a whole host of types. And small letter args is a function parameter pack that contains a whole series of objects of type specified and indicated in the capital args parameter pack in a position that is in accordance with its relative position in the function parameter pack. So what's going on here? This is a pack expansion, and what it's going to do is it's going to generate a series of comma-separated function invocations of the following form. Forward with t sub I, called with small t sub I. So t sub I represents the ith element of the template parameter pack, and small t sub I represents the ith element of the function parameter pack. And so that's, in terms of what's going on there, you just have to analyze it in isolation. It's essentially just going to generate a series of comma-separated forward invocations in accordance with the amount of objects or the amount of types in the template parameter pack, and also the amount of objects in the function parameter pack. And that is done by means of the pack expansion notation. And the presumption is the amount of elements in the corresponding, first and foremost, for this to be effective, there may be the logical constraint. Okay, firstly, there may be the logical constraint that there must be an equivalent amount of elements within the respective parameter packs for the pack expansion to be valid. And furthermore, for it to be semantically meaningful and useful, small args and the types of its elements should be captured in the template parameter pack specified as the explicit template argument to the forward function template. Now, we've already discussed the idea of reference collapsing and also how forward is implemented. We've already discussed R value references to template type parameters and also how forward is implemented, and in that way we can forward all type information in the original argument to some forwarded to function. And so that's what we're doing, because essentially we want a situation whereby if we pass an R value, let's just go back up to the function and place back. If we specify to place back an R value to the class type string, then in that case what we intend is for the move constructor to be invoked. And if we didn't employ this arrangement, the move constructor wouldn't be invoked. And so I'll give a brief description of how that works. Essentially, the idea is that if placeback is called with an R value, construct will also get an R value, such that it invokes the move constructor. And so the key observation is that if we pass an R value to and placeback, the type digest for t will be string. And so consequently, when we apply forward to the that type, we obtain an R-value reference to type string, such that construct will be called with an R-value reference. And so the construct function will in turn actually forward this argument to the string move constructor to build this element. And so the construct function in and of itself actually uses the same kind of mechanism to forward the original types of the arguments. And it's also implemented in terms of the erratic template mechanism to accept an arbitrary amount of objects of differing types. And if it's essentially, the idea is that in placeback constructs an element in the space directly managed by the container using one of the constructors. And the constructor that is used is the constructor corresponding to the arguments that were passed as the subsequent arguments to the in-placeback implementation. Now the constructor, the arguments passed, the subsequent arguments passed, must match one of the constructors of, in this case, string. Otherwise it's an error. And so in that way, we have added the in-placeback member function to our implementation, and in so doing, we are complete. That is our entire implementation complete for today. And so we implemented a relatively simple vector implementation that doesn't use the template mechanism to define a general solution. But there are a few more issues I would like to discuss. And the first point is that reallocation of a vector causes the invalidation of pointers and iterators in various contexts. And to see how that works, consider the following. If we were able to obtain a pointer that pointed to some location in memory that corresponded to the location of a particular object within the confinements of a dynamically allocated block of memory managed by a container, and that vector was in turn reallocated, then that pre-existing block of memory is going to essentially be freed and all the elements relocated to elsewhere in memory, such that the pointer now points to a location of memory that is essentially invalid. Thus the pointer becomes invalid. Okay, what else do I need to discuss before I end? So the next point I would like to discuss, one second. And again, I could go into more detail on these, but I'm trying to keep this as short as possible. Let me find the appropriate implementation to discuss this. It's going to be... Oh, we didn't write the equal sign for here. We'll do that now. I'm looking for reallocate. Okay, that's not there. Okay, so here it is. So reallocate was implemented in terms of a call to move. And in this case, we explicitly qualify it with std. Why is that the case? The very simple reason is that we essentially have to instruct the compiler to choose the move defined in the standard library, because the move facility is implemented in terms of an R-value reference to a template type parameter, and that's a single parameter, and it's going to return an R-value reference to the object passed to it. But as a consequence of the form that the parameter takes, it can accept any argument type, such that it is overly general and too permissive, such that if we were to define a custom move function with, a function with the same name but perhaps with different semantics, there would be a conflict. And so consequently we need some mechanism to differentiate, and we do that by means of explicit qualification. So that's the first point. And the last point I would like to make is as follows. Okay, so what I was going to discuss is that when reallocate is called in various different contexts, it is done so on behalf of the implicit disk parameter. And what I was going to do, and so consequently, we modify the representation of that object. And what I was going to do is find where the real. In fact, I know where it's located now. I was going to discuss it in terms of another function call, but we can do the following. In this particular invocation, we can see that we don't explicitly qualify this member function with an object upon which we initiate the operation. And so, upon what object is it being invoked? It's being invoked on the object upon which we initiated the initial call to some member function, such that it updates the representation of the object of the vector instance with which we are working. It updates this representation to point to a newly allocated block of memory. Okay, so that's today's lesson done. It was a relatively simple example today. We will introduce a more sophisticated implementation of vector in the following weeks. And I would just like to end on saying the following, which is that the next lesson will essentially be an overview of the C++ programming language, but that's going to take a few weeks to do. It's going to take a few lessons to do that. And in terms of how I'm going to be able to actually do that, it's probably not going to be this weekend, but the weekend after that. And it's going to include all the various different components that I have already discussed. And so all that has to be said now is I hope you learned something watching this lesson, if somebody's watching it. I hope you learned something. I hope you were enlightened as to one possible mechanism for implementing a vector, which is an entity for expressing a collection of objects, as was already indicated. I hope you found this lesson useful, and so with that, I will see you in the next lesson.